quiz, except there's going to be 8 or 10 of those, right? So you're going to have to work a little faster on the test. The first quiz is just to make you feel good. Oh man, this isn't that hard. So when you get the test, it's going to be the same kind of questions, but there'll be quite a few of them that you have to do, and you get 50 minutes. So today, okay, we had 10 or 12 minutes to do sort of one problem. On the test, you're going to get like 50 minutes to do 8 or 9 of those problems. So you can't be diddling around. You need to be able to go through it quick. Melissa can attest to that. No, just as a word of advice on the test, you get the problem you can't do, go on to the next one. Don't sit there and think about that one and ponder it for a long time. You aren't going to get behind. Move on to the ones you know how to do first. So, chapter 14. 14 is all about kinetics. And you probably haven't really seen much about kinetics in the first half of the year, in 13, 11, because it's kind of a separate subject. And it's different from most of the things we're going to talk about, even this semester. If you think about it, thermodynamics, and we have seen a fair bit, and we're going to see quite a bit more on thermodynamics, but thermodynamics is what tells us whether or not a reaction is energetically favorable. When we look at the free energy of formation, or if we look at the enthalpy, if those are negative, so that the products have less overall than the reactants, that tells us that the reaction will take place. So thermodynamics is all about whether or not a reaction will happen. Kinetics is all about how fast it will happen. If we look at thermodynamics, just because we know it will happen, we really don't know how long it's going to take. Some things can go really fast. Some things can take a very long time. And there's a lot of things that affect the kinetics. For instance, if you thought about, and I forget if they give this example or not. If you have a piece of aluminum, or aluminum foil, that aluminum foil, it'll get an oxide on the surface, but it takes it a little while and nothing very much happens. If I actually take aluminum and make really, really small particles of aluminum, and I expose it to air, it'll explode. They actually use aluminum particles for rocket fuel, because if I have enough surface area, then the kinetics will drive it to go very fast. And so even though the amount of energy per mole isn't any difference, the energy that happens to the speed of how the reaction takes place is drastically different. So kinetics is all about how fast reactions take place. So we're going to spend the next few days, hopefully by the end of this chapter, we'll understand some of these things about, what do we mean by reaction rates, sort of simple concepts from, sort of cartoons on how reactions take place. The things we're really interested in, though, are going to be, how do we actually determine rate loss? How do we know what's important in rate loss? First order kinetics and second order kinetics, or first order reactions and second order reactions, these are going to be really important. Most of the things that happen just sort of naturally that around you, they're either going to be a first order or second order reaction. So there are more complicated ones, but they're just not all that common. So we're going to spend most of our time just sort of thinking through some simple reactions for first and second order. If you think about it, reaction rates are going to be dependent on temperature, right? Most things. So do things happen faster or slower as the temperature goes up typically? Typically they happen faster, right? So by the end of this, using the Arrhenius equation, we should be able to predict. If we know the rate at one temperature, we should be able to predict what the rate's going to be at another temperature, if we know a few other pieces of information. So, we'll understand that. We'll talk a little bit about reaction mechanisms. Most of the time, these reaction mechanisms, very seldom can you come up with a unique reaction mechanism. We can come up with mechanisms that are consistent with how the rate behaves and how the reaction goes, but if there's some interesting intermediate that forms, sometimes that can be really hard to sort out. And then finally, we'll talk just a little bit at the end about catalysis and why catalysis is important. So, reaction rates. As we already said, thermodynamics tells us whether or not it will happen. Kinetics tells us how fast it goes. Thermodynamics is really all about the difference in energy between the reactants and products. That's all it is. And so as we go through this semester, we're going to talk about kinetics, we're going to talk about thermodynamics, and we're going to talk about how these things impact equilibrium. And hopefully at the end, it's all going to kind of make sense, and it's all going to make sense why we did it this order. Like it says, and like we just said, some reactions are fast, some of them can take a really, really long time. It does end up that reaction rates, even though, in the end, the thermodynamics is going to drive how much energy we put in or how much energy we take out. A lot of chemical processes, it's really all about how fast it goes. If you own a refinery, like Valero, if I can make the reaction speed up by a few percent, and I can increase the amount of output by 2%. So I'm making, 5 million gallons of gasoline a day instead of 4,900,000. That's a big deal, right? An extra 100,000 gallons of gasoline a day is a lot of money. So they spend a tremendous amount of time trying to figure out how to make reactions go faster. And so the whole industry, chemical engineering industry and all, is all about how do I increase reaction rates. There's lots and lots of people that get jobs doing nothing but try to improve reaction rates just a little bit. You can do that sometimes. What's the trade-off between making the reaction a little bit faster by going to higher temperature? Well, that takes more energy. If I can use something like a catalyst and make the reaction go faster, and then that catalyst, and we'll find out at the end, you just keep reusing the catalyst. So it's a one-time expense. Maybe that's a better idea. But so we're going to go through that a lot, and kind of think about how we can speed up reactions, and what sort of benefits it's going to have. And then finally, and at the very end of the semester, we're going to talk about radioactive decay. There's a chapter on nuclear chemistry. But radioactive decay is a great example of first-order kinetics. So a lot of the examples that we're going to talk about, just to demonstrate radioactive decay, or just demonstrate first-order kinetics, is going to be using radioactive decay. And the nice thing about it is, if it's first-order kinetics, the only thing that matters is how many atoms or how many molecules do I have to start with. In radioactive decay is a perfect example of that, right? If I have 100 atoms, half-life is 30 minutes. After 30 minutes, I only have 50 atoms left. After another 30 minutes, I only have 25 atoms left. So, if you know at any one time how many atoms I have or how many molecules I have, I know exactly how many of them I have at a time at the end. So, and the nice thing about radioactive decay is it's real easy to know exactly how many atoms I have. So it's a great example, and we're going to use that. The other part is because my background's in nuclear physics, so I like the example. So, we will see, and we're going to use this a bunch, as a great example of how to understand kinetics and what we mean by first-order kinetics. So, and again, this is really, really simplified, but I think, from the standpoint of thinking about how reactions take place, it's probably not a bad way to start. In terms of sort of this collision theory of chemical reactions. And what it really says, just sort of in the simplest idea is that, for a reaction to take place, either the atoms or the molecules have to get close enough together, they have to interact somehow, and after that, I may or may not get a reaction to take place. So what it really tells us then is that, the reaction rate is proportional to the number of collisions I have. So, if it really comes down to atom or molecule A and molecule B have to interact before they can react, the more times they interact, probably the more reactions I'm going to have take place. So, if we think about that, what are some of the things that can affect how often those reactions are going to take place? So what's one thing? How would, if I've got two gases, A and B, and I want to increase the reaction rate, what would be one way that I could increase the number of collisions? Yes, ma'am? Is that right? Think about it a little bit. If I increase the volume, what happens? Oh, decrease the volume. I'm sorry. Absolutely. So what happens when I decrease the volume? Well, they're going to collide because the pressure's going up, right? And so if the pressure goes up, the probability of them interacting is going to go up. So you have to decrease in the volume, which is increasing the pressure, will make it go up. What else? Heat. So what happens when I heat them up? Go ahead, you. Heat them up. You go.
Well, when temperature increases, the kinetic energy also increases, so it increases the rate of collision.
So it'll increase the rate of collision because as I heat it up, kinetic energy goes up, its velocity goes up, the average velocity goes up. So if they're moving around faster, the probability of them hitting each other. So there's two things when I heat it up. One, the probability that they'll hit each other will go up because they're moving around faster. Second is since they're moving faster, if they do hit, the probability that they might react will go up will go up also. So heat gives me two effects. So I can increase the pressure, I can increase the temperature. So there's two good things that I can do if I want to make the rate go up. If you think, this is sort of just as a rule of thumb. If you forget everything else you learned, or that you don't learn this semester, if you just think about it, and there's a reason, because it has to do with how the kinetic energy goes up as a function of temperature, reaction rates will double about every 10 degrees Kelvin. And that's not an absolute, but just, sort of as a first estimate. If somebody, you're out on the desert and you've got to make some reaction go and you're trying to figure out how to make it increase, 10 degrees higher, temperature will typically double the rate, some, roughly. So, if that was the case, you want to do the reaction during the day, not at night when it's hot, right? So, but so all of these things, what it comes down to is that the rate is somehow proportional to the number of collisions that I'm going to have per second. So if I can increase the number of collisions. Now, that's not taking into account things like catalysis and all that. It just is a really rough explanation of what goes on. If I can increase the number of collisions per second, I'm going to make the rate fly. So, the other piece of this is that, and again, this is kind of cartoonish, so it's not quite right. There's more that goes into this. But, we said, okay, we want to increase the number of times that the two molecules run into each other. The other thing that has to happen is that, for the molecules, for actually a reaction to take place, the molecules, not every time they run into each other are you going to get a reaction. There's a lot of things that have to go on that help them get close enough together. But even when they get close enough together, there might be some preferred orientation. In this particular reaction, they give this example that, okay, I have a chlorine atom with NOCl. If they react correctly, and this chlorine atom comes in and hits this chlorine atom, which is in NOCl, after the collision, if everything's right, I'll get a Cl2 molecule and I'll get an NO. So, in this particular case, it's not only they had to run into each other, they have to run into each other and sort of be oriented in the right direction. So part of all of this is this idea of having effective collisions. The probability that a collision is effective really all gets tied up into this terminology that we use, activation energy. So, that's the minimum amount of energy required to initiate a chemical reaction. So there's a bunch of stuff in that. But basically, activation energy just tells us that, we're going to have a bunch of times that the molecules run into each other. A bunch of times nothing will happen. If I'm at the proper energy, proper orientation, all these things, that, if I'm above the activation energy, then the reaction can take place. So, in this example, what we do is that we say, okay, orientation is certainly a critical piece, or an important piece. They have to be lined up correctly. Because I can have the exact same reaction. I have a chlorine atom come in. In this case, instead of hitting the other chlorine atom, it hits the oxygen atom. At least for this reaction on the Cl2, probably not going to happen. So that would be an ineffective collision. It's ineffective because the orientation is wrong. It might be ineffective because the energy was too low too. Even from the other way, if the orientation is correct, but the energy is not high enough so that chlorine atom can get in close enough, it still may not happen. So, this whole idea of collisional theory, the piece I want you guys to take away is that, yeah, it's important how many collisions I have, but it's also that the collision has to be the right kind of collision. So just increasing the number of collisions, it will increase the rate, but not every collision is going to be effective. So not every collision is going to lead to the product. And so a lot of times I'll just have, either these elastic scattering events or inelastic scattering. When it comes in, bounces off, maybe I've imparted some energy to this one. Really simplified. There's a whole lot to, how to sort of understand how the reactions take place. But this is probably, a pretty good starting point to be thinking about what affects the rates of reaction. So, and you guys have probably seen these potential energy diagrams before, but, what this tells us is, in this collisional theory, that, when I have two reactants come together, the whole thing that limits the kinetics is this activation energy. I have to have enough potential energy between these two guys that they can get to this activation energy or above this activation energy in order to make this intermediate state or transition state. And in this particular case, that transition state says, gosh, this chlorine atom is sort of stuck to that chlorine atom. I've had enough energy to get it to that point. Then as it goes downhill, I get the chlorine molecule to form, I get the NO to form, and the reaction is taking place. But if we look, what happens is that this activation energy, the bigger the activation energy, the lower the rate. Because if the activation is really big, most of these molecules don't have enough energy when they run into each other to get over this activation barrier, and so they never get here. So the kinetics is all about how big is the activation energy. Thermodynamics is all about how big is the difference between, in this case, reactants and the products. So what happens, and we'll talk about this more in a few days, for a catalyst, the catalyst doesn't impact thermodynamics. The energy difference between reactants and products stays the same. What the catalyst can do is get the activation energy lower, So instead of being this much energy, if I can lower the activation energy to there, more of the molecules have enough energy, more can go over the barrier, and so the reaction goes faster. So it doesn't change the thermodynamics, it just changes the actual rate. Okay? So, so we've kind of been talking about rates and how they work, at least conceptually. So, in the end, it's really only useful if we can calculate or determine the rate. Because, at some point we're going to say, okay, if I have this many molecules or this many moles of molecules, how long is it going to take for this reaction to take place? So, we really do need to come up with a way to quantitatively describe, how the reactions work and how they take place. So, if I have the really simple reaction, A goes to B. So, in this case, that's about as simple as it gets. And, and in this case, this would be a great example of radioactive decay. I have, a radioactive element like cobalt-60. Cobalt-60 then decays to nickel-60. But the thing, we can describe this, we can do it one of two ways. We can describe it as, okay, what's the change in the concentration of A as a function of time? We always end up with this negative sign out in front for the reactants because of the number of molecules or atoms of A is going down with time, right? Because they're being used up. But I can also explain it, because it's a one-to-one ratio, as, the change in concentration of B as a function of time. Because as A is being converted to B, if I know one, I know what the other one is. So, just sort of thinking about how am I going to explain that then? If I look, and if you take the time to count these, I think there's supposed to be 40 atoms of A there. So at the very beginning, we don't have any B. We've got 40 A atoms or 40 A molecules. After a certain period of time, you can count them up. And then you know that I went from 40 to however many is left, 30 or whatever, over just a brief period of time. So it's the change in A over that time is what the rate is. So same then for B, with a minus. For B, B is the red one. If I count up number B, I had 0. I go to that many. I take the difference, divide by time, and I get the rate of the product. So, the rate is only about how do I quantitatively describe how fast this reaction is taking place. So A decreases, B increases. So, if I were to plot this, and again, doing the A and the B, for A molecules, start out with 40 of them, at 10 minutes, over 30. So, you'd say, well, gosh, okay, well, we lost 10 in the first 10 minutes. Should you lose 10 in the second 10 minutes? No, because the number of A that we started out with is less, right? So, for the next 10 minutes, we lose 7 or 8, and then we lose. But as we keep going on in time, the amount of A that's being converted to B is going to be less, because there's less A than we're starting with. For B, we started out, we didn't have any, and it just keeps, so B increases. When A has to go down by 10, B has to go up by 10. A goes down by 8, B has to go up by 8. So the 2O, since it's first order in this case, the sum of it always has to come out to 40 because A is converting to B. We're not losing anything. But, if you plot a reaction like this, you'll get something exactly like this, and, it sort of asymptotically is going to approach 0. Because in reality, when I only get down to one molecule, the probability of it being converted will get really low. It's going to take a long time for that last one to get converted. So, the change in concentration is linear, but the change in atoms is not, right? Because I keep having less. So, this is one way that people will, describe a lot of times how to try to quantify what the reaction rate is. So, sometimes the hard part is trying to figure out, how do I actually measure what the concentrations are as a function of time? And it just depends on, radioactivity is an easy one because I can just use a counter and, however many decays I'm getting tells me exactly what the rate is. For other reactions, sometimes it can be a lot harder. In this case, this is one that we can use color to try to track what the reaction rate is. So if we look, if we take bromine and put it in acid, formic acid, what happens is that the reaction goes to 2 bromide ions, 2 hydrogen ions, and CO2 gas. It ends up that bromine, liquid or bromine in an aqueous solution is red. So when the reaction starts out, and we mix these 2 guys together, it looks pretty deep red. As we go on in time, and the bromine is being used up, the color gets less, the color gets less. Finally, there's so little bromine left that we can't even see it anymore. But if we had a spectrophotometer or a spectrometer and could measure the absorption of light for bromine, we can measure the concentration. We'll show you this in a second. We can measure the concentration of bromine here, here, continue to do that, and then we can try to figure out what the rate would be. So, if we look, one of the ways that we express the rate, we can say, how is the bromine concentration changing? So, if we measure the bromine concentration here, we measure the bromine concentration here, so final minus initial, divided by the 2 times, how long did it take from time 0 to when it hit, we would have, which should be BR2, we would have the concentration of bromine, change in concentration of bromine, divided by the change in time. And, so experimentally, we can actually then calculate what the average rate's going to be. One of the problems with this is that it's an average rate we get, right? Because it's over some finite period of time. We're going to talk a little bit next time about how we really want to get the instantaneous rate. We'd like to know when I have this many atoms of bromine in this reaction, how fast is it going to take place. But the other thing that you can think about, in this case, we're measuring the bromine concentration because it's pretty easy to measure, how red it is. But we could get the same answer if we measured the concentration of formic acid. So it'd be the same thing. The formic acid concentration, final minus initial divided by R. The other thing we can do is measure the product. We can somehow measure the Br minus or the H plus or the CO2. Any of those will get us back to being able to determine what the rate is, right? So, so you can express the rate any way, depending on what the different things that we have. So next time we'll start off and we'll do problem 14.8 because they kind of gives us a way to write the rate. Okay. Yeah. Got a minute left.